Aloha, everyone. Today, we're going to talk about projectile motion, at least the first part of it. Part 1. Horizontal launch. Now, you might remember that if a ball rolls off a table or if a projectile is launched horizontally, we did a little testing of this, and either using a simulator or maybe yourself, you realized that the time that this projectile takes to reach the ground, as long as you're launching it exactly horizontally and exactly level, does not depend on how fast you launch it. It's always going to accelerate at the same rate. It's always going to fall to the ground in the same amount of time. So it doesn't matter if you roll a ball off slowly or quickly. No matter how fast you roll the ball off the table, it will still take the same amount of time to reach the ground. What do I mean by that? Take a look. So because of that, we have a key principle that we need to know when we are dealing with motion in 2 dimensions. What I mean by that is motion where an object is moving both horizontally and vertically at the same time. And the key principle of this is motion in 1 dimension does not affect motion in the other dimension. And I guess I should put an S there because we are in a 3-dimensional universe, but in 2 dimensions, 1 dimension doesn't affect the other dimension. In 3 dimensions, one dimension does not affect the other 2 dimensions. So, okay, if we have this, what do we mean by that? Well, if we have a table here, it doesn't matter how fast it's rolling this way, it's still going to hit the ground based on the vertical distance because that's the way it needs to travel when the ball is moving. When the ball is moving, it needs to travel vertically to hit the ground. So how fast it's moving horizontally doesn't matter. So what does that mean? Well, that means we're going to have 2 sets of kinematic variables. We're going to have a set of kinematic variables for the horizontal direction, and we're going to have a set of kinematic variables for the vertical dimension. And we're going to have to keep those separate. Whenever we're working on a problem like this, I suggest we draw a table. And that table should have the following things: the displacement in the x direction, the displacement in the y direction, the initial velocity in the x direction, the initial velocity in the y direction, the final velocity in the x direction, the final velocity in the y direction, the acceleration in the x direction, and the acceleration in the y direction. And finally, the only one of these that is not a vector and therefore does not have a direction is going to be time. So it turns out time is the only variable in this entire set of 1, 2, 3, 4, 5, 8, 9 variables here. In this entire set of 9 variables, time is the only one that affects both of the dimensions. So time is the only variable we can use with either the set of y variables or the set of x variables. But we don't ever want to mix the 2. For instance, if I have a distance in the x and a velocity in the y, I can't use those in the same equation because 1 dimension does not affect the motion in the other dimensions. So we're going to start off by building tables like this. Let's imagine that we have over here, I kind of drew a table here. Let's say there's a ball here, and let's say it's launched with an initial velocity. We roll it with an initial velocity of 2 meters per second. And let's say the height of this table is, I don't know, 1 meter. And I want to know how far away does the ball land? Well, I'm going to start by looking at the variables and trying to fill in the pieces that I know. So we were given an initial velocity. And that initial velocity is the ball rolling across the table horizontally. So that is an x variable. Well, I should probably label it. I'm going to call this way positive x. And I'm going to call downward positive y because the ball is not going to go upward here. Everything is going to go downward. So I feel like I'll save some negatives by doing that. The rule is you can choose up or down, left or right, whatever you want. You can choose at a weird angle if you want, but the two dimensions have to be 90 degrees to each other. And I didn't draw it well here, but pretend that's a 90-degree angle. So x is going to be horizontal, y is going to be vertical. Okay, the initial x here is going to be 2 meters per second. I also know that the height over here of the table is 1 meter. That's going to be the displacement in the y direction. So dy is going to be 1 meter. And the ball goes from the top to the bottom, so it goes downward, so that dy is positive, because we said downward was positive. Okay, there's a couple other things we know. We know the acceleration in the y direction is going to be gravity. Gravity's got to be pulling on it, so this has got to be 9.81 meters per second, and it's downward. So since we said down was positive, that number is going to be positive. We also know the acceleration in the x direction. What do you mean by that? Well, nothing's pulling on it horizontally. Once it leaves the edge of the table, the only force acting on it is gravity. So therefore, as it's falling, there is no horizontal acceleration because there is nothing to pull on it. So ax is going to be 0 meters per second. There are no other forces acting on it, therefore an object in motion stays in motion. Since there's no other forces, it's going to keep doing that until something changes. Okay, so we have ax and ay are going to be good. There's another variable we know, and that's v initial in the y direction. As the ball's rolling across the table, and the instant it leaves the table, is the ball moving up or down? No, it's only moving sideways. So because of that, v initial in the y direction is going to be 0 meters per second. Now, that'll get more complex when we start launching at an angle, but as long as we're leaving the table horizontally, as long as we throw a projectile horizontally, as long as we launch it horizontally, it's going to be 0. All right, so now I have 3 variables in one of my directions. And remember, we need 3 variables in order to solve anything. So you can see here in my y direction, I have 3 variables. If I take those 3 variables, I can solve for time. And once I have time, I have 3 variables that I will be able to use in the x direction. And from those 3 variables, I should be able to solve for dx. So we're going to use, and I'm just going to put a little comment here. It's a good idea to keep yourself organized, to write a little comment here about how you're going to solve this. So we are going to use the y dimension, to solve for t. Okay, I have a dy, I have a v initial y, I have an ay, and I'm looking for time. To me, that sounds like what we called kinematic equation number 3. That's this one. Distance equals v initial t, and this is displacement, plus 1/2 at squared. These are all vectors, which means I need to be careful about this. Am I using this in the x direction or the y direction? We're using this in the y direction, so I'm going to put little subscript y's on each of these vectors. Y and y. Now it looks a little bit more intimidating, but don't get worried. It's not bad. Those y's are just reminders that you can't mix these with the x variables. So nowhere in here should we see this 2 meters per second. We should not substitute that in. We can't substitute this into this equation. We can only use the y variables over here in order to solve this equation. So let's see here. I need to solve this for t. And I know one important thing. Solving this for t is awful if you have a v initial that's non-zero. But here v initial is 0, so this piece isn't going to matter. V initial times time is also 0, so everything before the plus turns into a 0. So this is going to be dy equals 1/2 ay t squared. Vector there, vector there. Solving this for time, we've done this before. I'm going to multiply by 2. dy equals ay t squared. I'm going to divide by ay. 2 dy over ay is equal to t would be squared. So I'm going to take a square root to get rid of the squared. And there we have our formula for time. So now all we need to do is plug in some numbers. It's the square root of 2 times our distance in the y direction is 1 meter, divided by acceleration in the y direction is 9.81 meters per second. And this is going to be equal to, I'm going to call that 0.45, round that to a 2 seconds. So there is the time that it takes for this object, for this projectile, this ball, to roll off the table and fall to the ground. And it doesn't matter how fast it was rolling horizontally, every single time it's going to fall in that amount of time, as long as that table is 1 meter tall. So now I can take that number and I can place that into my table with time. 0.452 seconds. Now I have v initial x, acceleration in the x, time, and I'm looking for distance in the x direction. So if I wanted to find distance in the x direction this time, I'm going to need to use another kinematic variable. And to me, it sounds like, or kinematic equation that is, and it sounds to me like we're going to use kinematic equation number 3 again. But this time we're going to use the x direction to find distance x, or displacement actually. Okay, so we're going to find dx. How far did it go horizontally? So kinematic equation number 3 says this. Distance is equal, displacement is equal to v initial t plus 1/2 a t squared. This time, instead of y's running around everywhere, this time we're using the x direction. So I'm going to put x's on these to remind myself that I cannot use the y variables. I must only use the x variables here. So let's plug in some pieces here. It turns out I'm looking for dx. It's already solved for it, so all I need to do is plug in some numbers. So distance in the x direction is equal to, displacement in the x direction, is equal to v initial x was 2 meters per second. 2 meters per second. Times a time of 0.452 seconds plus 1/2. Acceleration in the in the x direction was 0 meters per second. Oh, so that turns out everything after the plus isn't going to matter. Times a time of 0.452 seconds squared. So this piece is 0. So this piece times this piece squared and times that. All of this turns into a 0. So it's not going to matter. So really all I need to do is multiply those two numbers. And I get distance or displacement x is equal to, let's see, times 2. 0.903 meters. Bam. Now we could use kinematic equations to find the other pieces of this table, like v final and v final x and v final y. But we're not going to worry about that just yet. Really, all you need to do is use another kinematic equation, pick a different equation, find v final x or v final y. That should be a piece of cake. The key is if they ask you for the final velocity or the angle of impact. The key to that is if they ask you for final velocity, what is the final velocity? Well, to find the final velocity, if they don't tell you horizontally or vertically, or in the x direction or in the y direction, or something that tells you in one of those two, then they're going to ask you to combine them. But since these are vectors, we have to be careful about how we combine them. V final x is going to be going this way. And V final y is going to be going this way. So when we combine these two vectors, we're going to have to figure out what is this. This will be V final. So clearly, you can see you can use the Pythagorean Theorem here. A squared plus B squared equals C squared. Or maybe you can write it like this. V final is equal to the square root of V final x squared plus V final y squared. So all I did was I solved that. The V final is C. All I did was solve for C and plug in V final x and V final y. So this will tell you what the final velocity is. And if you want to know the angle of impact, if they ask you for angle of impact, they're actually asking for this angle out here. Call that theta, which is the same as this angle up here by geometry. So if you're looking for the angle of impact, if I'm looking for this angle up here, I can use tangent in order to solve for that. Actually, inverse tangent or arctangent. The angle of impact, theta, is going to be equal to the inverse tangent of V final y over V final x. So you can use these two equations to solve for the final steps if they ask you for the final velocity without saying in the x direction or in the y direction. And if they ask you for what is the angle of impact, what direction is it going when it hits the ground, it's the inverse tangent of V final y over V final x. So really that's all there is to it, to projectiles that are launched at a horizontal angle, that are launched horizontally. Next time we'll talk more about projectiles and see what happens when you start to change the angle. Mahalo for watching, and see you next time.